Yeah, good evening, all. Myself, Dr. Praveen, Associate Professor in School of Computer Science and Artificial Intelligence, SR University. Today, I'm going to explain AVL trees in data structures. Okay, in last video, we discussed binary tree, binary search tree, and what are our binary search tree traversal techniques we completed in last video. So in this video we will discuss AVL trees. So why we learn AVL trees? What are the advantages to use the AVL trees? So in binary tree, there is no specific condition. Okay, you know the tree is a collection of nodes. Binary tree means a root node has contain at most two chairs. And next one is the binary tree, the time complexity will increased. So that's why we move from binary tree to binary search tree. In binary search tree, the time complexity will be reduced. So why the time complexity will be reduced? Okay, here we have a specific condition. Based on this condition, the elements are less than root node, then we shift to the left side. The elements are greater than root node, then we shift to the right side. So this is the basic property of binary search trees. Now coming to AVL trees, AVL trees is always follow the balance factor. Okay, now the binary tree where for every node all vertices binary left subtree is smaller and all values in the right subtree is larger. So now for example, sometimes we have a left skewed tree and right skewed tree. In left skewed tree, all elements are less than the root node, and right skewed tree, all elements are the greater than the root node. So in this situation, if you want to traverse or if you want to search a element, then we move to only left side or we move to only right side. That is the drawback in the binary search tree. I want to take a small example here. For example, the elements are The elements are 1, 2, 3, 4, 5, 6, 7, 8. We assume. Now, how can we write how can you draw the binary search tree? So, 1 is the root node, 2 is the right child of 1, 3 is the right child of 2, 4 is the right child, 5 is right child, 6 is right child, as well as 7 is right child, and 8 is the right child. So, now this is called the right skew tree, because all elements are only right side. Okay, now we have to search 8. We assume 8. So 8 is comparing with the root node. 8 is greater than root node, so we move to right side. And we compare with the intermediate root node, that is 2. 2 is equivalent to 8. No. Then 8 is greater than root node, so we move to right side. And again we compare with the 3. 3 equivalent to 8. No. 8 is greater than 3, so you move to right side. 4 is comparing with 8, 5 is comparing with 8, 6 is also comparing with 8, 7 is comparing with 8, and 8 is comparing with 8, 8 equivalent to 8. So element is found. So now observe here. So if you want to search 8, then the time complexity is very high. So how many elements we have? 8 elements. So the time complexity for 8 is 8 ms. 8 ms means it takes 8 iterations. So this is the drawback in the binary search tree, as well as now we have to write 8, 8, 7, 6, 5, 4. Next one is the 4, 3, 1. How can we draw the binary search tree? Now 8 is the root node, 7 is left child, 6 is left child, and 5 and 4 and 3 and 2 and 1. You observe here, this is the left skew tree. Left skew tree only we have the left elements. There is no right elements. So now this is also binary search tree, but only we have a left elements. So now we want to search 1. For example, we have to print the 1 or we want to search 1. Now 1 is leftmost child of 8. So 1 equivalent to 8, no condition is failed. 1 equivalent to 7, no condition is failed. 1 equivalent to 6, no condition is failed. Then move to the left side. Next to intermediate root node is 5. 1 equal to 5, no condition is failed. And 4 with comparing, 3 is with comparing with 1, 2 is comparing with 1, or 1 is comparing with 1. Finally, 1 is one is available in the last node. So these are the drawbacks in the binary search tree. Okay, if you have a left skew tree or you have a right skew tree, then the time complexity will be increased. So that's why we are moving from binary search tree to AVL tree. AVL stands for Adelson, Welsky, and Landis tree. So these are the scientist names. Okay, AVL is a balanced, self-balancing binary search tree. AVL tree is a binary search tree, but all binary search trees are not AVL trees. You remember this point. A self-balancing BST, where the height differences balancing factor between left and right subtree is at most 1. So that is called HL minus HR is less than or equal to 1. Height of the left subtree and minus height of the right subtree. Okay, we construct the left subtree and we construct the right subtree. Now we compare with heights between left and right. It is always less than or equal to 1. So that is called the binary search tree. Now, AVL trees is a height balanced or self-balanced binary search trees. AVL is the height balanced or self-balanced binary search tree. Okay, what is height balanced? That is called HL minus HR is less than or equal to 1 is the height balanced. That means an AVL tree is also binary search tree, but it is a balanced binary search tree. It is a balanced binary search tree. Okay. Now, a binary tree is said to be a balanced if the differences between the height of the left subtree and right subtree of every node in the tree is either -1, 0, or positive. That's why the balancing factor is this is the balancing factor -1, comma 0, comma +1. For every node in an AVL tree, balance factor belongs to -1, 0, +1. In an AVL tree, every node maintains an extra information known as the balance factor. Okay, balance factor that is -1, 0, and +1. In an AVL tree, every node maintain an extra information known as the balance factor. That is you written here. You written here -1, comma 0, comma 1. The AVL tree was introduced in the year of 1962 by Adelson, Welsky, and Landis. These are the three scientist names. Now, 1962, the AVL tree is invented. Yeah, key characteristics of the AVL trees. The first one is the self-balancing, and the next one is the balance factor. Third one is the rotations, and fourth one is the logarithmic time complexities. Self-balancing, you observe here, these are the four characteristics: self-balancing, balance factor, rotations, logarithmic time complexity. Now, self-balance factor. Okay, already we discussed balancing, that is called mod HL minus mod HR is always less than or equal to 1. For every node in an AVL tree, balance factor equal to height of the left subtree minus height of the right subtree. Height of the left subtree minus height of the right subtree. Possible values of the balance factor, that is called minus plus 1, plus 1, 0, and -1. Left subtree is taller, that is +1. Both subtrees are equal height, that is represented with 0. Right subtree is taller. Okay, left subtree is taller, then that is represented with the 1. Right subtree is taller, that is represented with the -1 because HL minus HR. Now, if balance factor is less than or equal to 1, the node is balanced. If balance factor is greater than 1, the node is unbalanced. And rotations are required to restore the balance. Okay, so you observe here, less than or equal to 1, there is no problem. Now the left subtree and right subtree both are in the balanced. If balance factor is greater than or equal to 1, the node is unbalanced and rotations are required to restore balance. So this is the balance factor. And next one is the balance factor. That is balance factor equal to height of the left subtree minus height of the right subtree. Okay, height of the left subtree minus height of the right subtree. So now coming to this example, this is the AVL tree. We check whether it is AVL tree or not. 100 is the root node. First one you observe here, AVL tree is a binary search tree. AVL tree is the binary search tree. 100 is the root node and 50 is the left and 150 is right child and 25 is less than 50. So that's why we move to left side. 75 is greater than 50. That's why we move to right side of 50. And you enter the 65. 65 is less than 75. We move to left side. And 85 is greater than root. So we move to right side of 75 as well as 125 and 175. So now you observe here all leaf nodes. These are all the 0. All leaf nodes are 0. Now this is 1 and this is 2. Right now and next coming to this also. Now this is 1 and this is 0. Balance factor 0 is perfectly balanced. So now coming to this one. This is the subtree. Now what is the value here? This is 1, this is 0 and 0. So no problem. And they coming to this one. Now 0, 1. 0 minus 1. What is the value? Minus 1. And next coming to this one. 0 and this is 1 and this is 0. So no problem. This is also balance factor. And now coming to this one is now this is 0, this is 2 and this is 3. 3 minus 2. Yeah, because we have a height. This is you continue 0, 1, 2, 3. You observe here. 65 is 0, 75 is 1, 50 is 2, and 100 is 3. So 3 minus 2, the value is equivalent to 1. So this is the perfect balanced binary search tree. Right? Now example 2, construct AVL tree with the following nodes. Okay, now this is the 15, 18, 8 and 18, 5, 11, 17 and 4. Okay, now if 12 is the root node, 8 is the left child, 18 is the right child. So we can construct 12 is root node, 8 and 18, and this is the 5, and this is the 11, and this is the 17, and this is the 4. Now you observe here, this is not balanced. So, okay, now height of the left subtree is height of the left subtree, and you compare with the height of the right subtree. So we check whether it is balanced or not. Check whether it is balanced or not. Okay, now you observe here. So initially 0 plus 1 and 1, 1 minus 0, 1, and next one is 0, 1, 1 minus 1, 1 minus 1, again 1. So this is the balancing factor. And now this example is not balanced. Okay, you construct the balanced binary for this example. Now you construct this example. This is the third example. Now in this example, now you have to already we completed example 2. Now example 2, this is the AVL tree. There is no problem in the example 2. Now check, now this is the AVL tree example. Now the third example, 20, 11, 5, 32, 40, 2, 4, 27, 23, 8, 28, 5, 50. So which is the root node here? 20 is the root node. 11 is the left child and 5 is the right child. 32 is the right child. 40 is the right child. And 2 is left child. And 4 is the right child of 2. And 27 is the 27 is this is the 27 and this is the 28 and 50. Yeah, sorry, 40. This is the 40 and this is the 50. Now you observe here, this is 0. Now this is 0. Now this is 1. Okay, continue. Now elements are check the height of the left subtree and height of the right subtree. Now insert 7 and 2 for previous binary search tree, then check it whether it is balanced or not. Every time we have to check whether the root is in balanced or not. How we check the root is whether it is root balanced or not? We take the left subtree and right subtree. Okay, left subtree and right subtree. And left subtree means first you take the left element and right element. Whether the left element and HL minus HR equivalent to 0 or minus 1 or 1, then that is in the balance. So now coming to this one, 2 is the left child, so that is 0, 4, 1, and 7 is also 0. Because why 7 is also 0? There is no left child, there is no right child. That's why it is 0. Now 1 minus 0, the value is 5. This is 1 minus 0, HR minus HR. So this is 1, this is 0. 1 minus 0, 1. Okay, next one. Here there is no left child, there is no right child. So now this is the height is the 2. So again, this is also in balancing. And next one is, so next this is for the first example. Okay, now this is also in the balancing. Okay, now again we have to check. Now we check whether it is balancing or not with this example. You try to solve this example. Now this is the and properties of AVL trees. It is a binary search tree with additional balancing procedure property. And if there are n nodes, the height of the AVL tree is always big O of log n. The balanced binary search tree is a AVL tree. That how it is check whether balanced or not. You already know height of the left subtree and height of the right subtree. This guarantees that such insertion and deletion operations are efficient. Height of the AVL tree is big O of log n. When the operations insertion operation, that is take the big O of log n, and deletion big O of log n, as well as such also big O of log n. Both the all three operations time complexity is the big O of log n. And every AVL tree is a binary search tree, but every binary search tree need not be AVL tree. Already we discussed. Every AVL tree is how it is binary search tree. So the first we search the balancing factor. After then whether if it is not balanced, then we have to go for the rotations. Okay, AVL tree rotations. In AVL tree, after performing operations like insertion and deletion, we need to check the balance factor of every node in the tree. If every node satisfies the balance factor condition, otherwise we must make it balanced. Whenever the tree becomes imbalanced due to any operations, we use rotational operations to make the tree balanced. So these now why we need balancing. If your tree is not balanced, so we can go for the rotational techniques. So rotation is the process of moving nodes either to left or to right to make the tree balanced. Okay, balancing. So there are basically 4 types of rotations which are also. Okay, this is important balancing rotations. Now left rotation, right rotation, left rotation, right left rotation. So rotations are 2 types. First one, single rotation, and double rotation. Single rotation, again we have 2 types. Sorry, single rotation, again we have 2 types. That is the left rotation and right rotation. Double rotation, we have 2 types. That is one is the left right rotation and right left rotation. This is these 2. 3 and 4 is the double rotation. 1 and 2 is the single rotation. Now we will discuss these rotation techniques. Operations on the AVL tree. One is the best of main operation is searching, and it is the same as normal binary search tree. As an AVL tree is always a BST, so we can use the same implementation as by BST. The advantage here is a time complexity is the big O of log n. So what is the searching in our BST? Simple, if the element is less than equivalent to root node, root data, then we print the element, return the root data. Otherwise means we have two conditions are there. One is the if the element is less than the root data, then we can move to the left. That is called move to the left side. If the element is greater than the root data, our searching element is greater than the root data, then we can move to right side. We have two conditions. One is less than, other one, second one is the greater than. So that is the searching. It is also 100% similar to the AVL tree. And insertion, it does not rotation along with the normal BST insertions to make sure that the balance factor of the imbalance impacted node is less than or equal to 1 after insertion. Deletion, it also does rotations along with the normal BST deletion to make sure that the balance factor of the impacted nodes is less than or equal to 1 after deletion. Okay, when we are deleting the element in binary search tree, we can three approaches are there to delete the element. One is the root data deletion, other one only intermediate root data, and another one is the leaf data. When we are remove the leaf data, there is no problem. If you want to remove the intermediate root node, then the left most element is shifted to the root data, and if you want to remove the root data, then the right child leftmost element is moved to the root data. That is the three deletion techniques in the BST, as well as we follow the AVL tree also. Now, single rotation. Single rotations, we have how many single rotations? Two single rotations. One is the left rotation, right rotation. Double rotation, how many? Two types. One is the left right rotation and right left rotation. Now, first we will complete the single rotations. Left right rotation, the rotation, sorry. In LL rotation, left to left, LL stands for left to left. Every node moves one position to left from the current position. So this is the right skew tree. When we are use the right skew tree, see, this is the one is the root node. What about the left? Left is the empty. Only we have a right elements 2 and 3. Tree is imbalanced here. One of you check the left subtree is 0, 0 minus 2. So value is this is 0, this is 1, this is 2. 0 minus 2, 0 minus 2, then value is minus 2. So now in this situation, this tree is the imbalance. So now this tree is moved to balanced by using the one is moved to left. So observe here, left to left rotation. One is moved to left side. So now what about two? Two is moved to root node. So two is the root node. Two is the root node, and one is the left child, and three is the right child. So this is the left rotation. Okay. Now the second one is the left single rotation, right rotation. Right rotation, every node moves to one position to the right from the current position. You observe here, this is the left skew tree. Left skew tree. Now insert 3, 2, 1. Okay, what about 3? 3 is the root node and 2 is the less than root node. So you shift to left side. And next one is 1. 1 is the, okay, 1 second. Okay. Now, one is the left node, left, okay. Okay, left node. And this is called the left skewed tree. Okay, tree is imbalanced because nodes 3 has a balance factor. So now left 0, 1, 2, 2 minus 0. What, why 2 minus 0? Now this is the 0, 0. So 2 minus 0, 2. So now left it is not balanced. So what is the balance factor? Minus 1, 0, 1. But 2 is not in balance. So now to make a balanced, we use RR rotation, which moves one position to the right. So one is moved to here. First one, two is moved to root node. Two is moved to root node. Then automatically the one is also moved to root node. This is one R and this is another R. R right to right mode rotation. Now two, three is moved to here. One, two, this balance factor is perfectly balanced. So now, next one is the double rotation. In double rotation, we have again two rotations are there. One is the left-right rotation and right-left rotation. Left-right and right-left rotation. The left-right rotation is a sequence of single left rotation followed by a single right rotation. In left-right rotation, at first every node moves one position to the left and one position to the right from the current position. So now you observe here 3, 1, 2 is the element. So 3 is the root node. You observe here 3 is the root node, 1 is the left child, and 2 is the right child of 1. So this is there is no right to elements. So this is imbalance. Okay, so from this one we can move. So now one is moved to left, right. This is moved to left and this is moved to right. Observe here. This is moved to left. This is right, moved to right. So now from after this one, you observe here. After this one is moved to left and two is moved to here. So this is the left rotation. Okay. Left is completed and right rotation. Now one is moved to right and two is moved to right. Automatically three is moved to right. After right rotation, we get the elements in balance factor. So this is called the left to right rotation. Observe here. So first one is the left rotation. Second one is the right rotation. So finally left right rotation. Next one, we have another rotation is there, that is the right left rotation. Right left rotation. See, the right left rotation, we have the elements are single right rotation followed by the single left rotation. First, two is 1, 3, 2. One is the root node. Here we observe one is the root node. Now 3 is the right child and 2 is the left child. So this is the what about the left subtree? Left subtree is 0. So now 0 minus 2 value equal to minus. So this is the imbalanced. From this one, now you observe here right left rotation. First what should we do? Now single right rotation. Now 2 is moved to right one, single right, and 3 is moved to right. See, observe here. This is right R and this is right R. After right rotation, we get the elements 1, 2, 3. So now this is the right skew tree. Okay, again we use the now 2 is moved, 3 is moved to here, 2 is moved to here, 1 is automatically moved to left tree. So now 2 is the root node, 1 is the left child, and 3 is the right child. So this is called the left to left rotation. So finally, after right, after left, we get the right, left rotation. RL rotation is now battery is the balanced. So these are the 4 balancing trees. One is the single rotation, left rotation, and right rotation. Double rotation, left rotation, and right left rotation. Then I'll give AVL trees when the binary search tree becomes unbalanced. Balance factor is -1, +1, or 0. We perform rotations to restore balance while keeping BST property intact. So this is about the AVL trees. AVL tree is a balanced binary search tree. Okay, now this is the simple another example for the left rotation. You check this rotation. Now 30, 20, 10. 30 is the root node, 20 is the left child, 10 is the left child of 20. So now this is not balanced. So unbalanced binary search tree. So now 30 is +2. So we move here. Now 20 is moved to root node automatically. 30 is moved to right child. This is the left right rotation. Next one is the right rotation. So right rotation is nothing but a left rotation. Left rotation is nothing but a right rotation, just quite opposite. So 10, 20, 30. So left rotation. So right rotation 20 is moved to root node. 10 is also automatically left child. Okay. Left rotation means now 10 is moved to left. Okay, this is the perform after performing left rotation. 10 is the left element, 30 is the right element. Now left right rotation. So same example 30, 10, 20. So 30 is the root node, 10 is the left child, 20 is the right child of 20. 10. So now first we move to the left rotation and the right rotation. So left rotation, after left rotation, this is called the left skew trick. So 20 is move to root node. So 10 is automatically left side. So now step to right rotation, 20 is move to root nodes and 10 is the left child, 30 is the right child. And last right to left rotation, the example is 10, 30, 20. So 10 is the root node, 30 is the right child, 20 is the left child. Okay, now perfectly. After this right rotation, 10, 20 is the move to right side. Right? Now 10, 20, 30. Then 30 is move to left side. Now left rotation 10. So 20, 10, 30 balanced. Now such operation already we discussed. AVL such operation performed with the big O of log m. So the search operation in AVL tree is similar to the search operation in the binary search tree. Okay, this is about the AVL trees. Okay, finally we complete the AVL trees. Thank you. Thank you for your cooperation. Okay, next videos I will explain the B trees and B plus trees. Right. Thank you all. Now please support with the channel and please like and subscribe and share to your friends. Thank you. Thank you all.